It's my honor and pleasure to introduce our first keynote speaker, Amin Vahdat. I've known him since he was a professor at UC San Diego, but he's currently the vice president of Google, leading the ML systems and cloud AI. He and his team deliver industry-leading ML systems for Google and the world. Before that, he oversaw the Google's compute, storage, and networking infrastructure. His work has had tremendous impact both on the research and on industry and the whole world, actually. And for that, he's won numerous awards, including the SIGCOMM Lifetime Achievement Award for his foundational work on data center and wide area networks. And many other awards that I'm not going to talk about today. And he's a member of National Academy of Engineering and an ACM fellow. So it's my pleasure to introduce Amin.
Thank you, Madan. Let me see if I can get this to present. The Wi-Fi is a little bit spotty. We will go ahead and start, and I will count on the Wi-Fi hopefully kicking in. If not, you'll have a slightly reduced, wait, it's thinking about reconnecting, font size. Anyway, let's start with some bookkeeping. First, it's really a tremendous pleasure for me to be here. I'm excited to be presenting this material in front of you all. Some of it is very late breaking, last night, in fact, so hopefully you'll find it interesting. I did, and that's why we decided to go ahead and include it. Second, this work reflects the work of many, many folks. In other words, I'm really playing back to you the insights of others. Very little in this presentation reflects original insight on my part. Of course, anything that I do to screw up the presentation to you all, the responsibility is with me. And finally, I am going to be presenting a Google-specific view because that's the work that I know best. But I do believe that the trends are actually applicable across industry. But you'll excuse me for having it a little bit local within Google. Okay. So let's see. But really, what I want to emphasize, and you all are already seeing this, is that we really are at the beginning of a revolution. And what I want to say here is the time. Better? Can people hear me okay? Yep, great. Okay, so the I'm getting, you want me to, I can speak louder. Does that help? Yeah, okay. I will try to enunciate more and speak with more volume. So the time that I'm actually most reminded of, actually at this point, is 1993. This is when actually I saw NCSA Mosaic running on top of the World Wide Web. Right? And this was probably the beginning of the internet as a force for all of the planet. Right? And now, it started with relatively humble beginnings. Right? But even in that time period, many of us in 1993 could see the tremendous impact that this would have, right, across industry, but also across society. And we'll talk about some of the strides that we've made over the intervening, let's say, 30 years to today, from relatively humble beginnings. We're at a place now where we essentially have the totality of human knowledge available at our fingertips. And this is a radical change in terms of how we think about society, actually how we think about technology. I think that the change that we're witnessing with generative AI today is at least as big, if not bigger. And what I'll predict based on history is that our ability to predict exactly what's going to happen and how radical the transformation is going to be is actually rather limited. But the next 5 years, 10 years are going to play out some really, really exciting changes. And this community, actually, the infrastructure, the architecture community, is going to be central. Because the playbooks that we've developed over the past, let's say, 25 years or so, are no longer going to apply. And so I'll go through some of that history as well. One thing, again, that I want to point out as something perhaps for this community to consider, it hasn't yet hit, but I actually do see robotics as being a really big transformation as part of generative AI and as part of artificial generative intelligence. In other words, think not in terms of how people interact with technology just via chat or text, but how people interact with technology via autonomous agents that have access to multimodal input. That means audio, video, images as input and output as well. And the implications here from a systems perspective, from a responsibility perspective, from a safety perspective, are going to be profound. And maybe one of the main things I'd love to leave this community with is that treating responsibility and safety as a first-class technical requirement that we build in from the ground up and not attempt to retrofit is absolutely a critical requirement, right? We're accustomed, starting with me, by the way, to think in terms of how do I make things faster? How do I make things more efficient? Right? It's super fun. It's rewarding, right? You have a number to go after. But I would say, as importantly, more, how do we build in capability for responsibility and safety into this technology so that we can build the right systems moving forward? And I think actually that starts perhaps more than any place else with the research community. I think this community has all the right incentives to go after these critical problems from the ground up. Okay. So I also want to point that we are on this journey, not toward generative AI, but artificial general intelligence. And the definition I like for AGI is a computer system that can do most tasks of economic value as well, or perhaps better than humans. Now, this is a scary proposition, but I think also an exciting one, because if properly harnessed, this can really be a multiplier for human creativity and capability. And again, all this is the infrastructure that's going to power responsible artificial general intelligence is going to require transformation. And so, in other words, it's no longer nice to have, it's required. This is going to transform everything. I'm not going to spend time on this, but I'll point to two of my favorite examples from personal experience. And that is a teacher for every student and a doctor for every patient. As a former professor, I really love the mission of education, sincerely, miss it tremendously. Thinking through how to scale that and how to really touch all learners remains a grand challenge, right? And one that I struggled with as a professor. One of the places I've realized over the years that I've been very fortunate, for example, is that I was good at learning the way that universities like to teach. But that's not true for everybody. And that means that a lot of people, a lot of very, very, very capable people get left behind. And to me, that's not right. And so now the opportunity here is, how do we actually, and think in terms of many of you probably teach in one way or another, perhaps as graduate students, perhaps as faculty, perhaps as mentors. One of the key things is, how do we, as a teacher, when you are able to work one-on-one, one-on-two, one-on-three, one of the things you do is adapt to the people you're speaking with, you're working with, dynamically. You have lots of experience. And you know what's getting through, you know how to explain things, you know how to connect with them. What would we do to be able to scale this? Your capabilities, your collective capabilities. I don't think this is about replacing teachers. We don't have nearly enough teachers. This is about augmenting teachers. And I'll say the same thing. You can imagine how that analogy applies to doctors, right? For those of you who've been fortunate to have good healthcare, how transformative that can be. And for those of you who struggle to get good healthcare, how frustrating and hard it can be. Okay, so what drives these fundamentally new requirements? And why is it that we're in a place where we have to reinvent? I refer to these changes, these really sea changes, as the 4 S's. One is societal infrastructure. I'm going to go through each of these quickly. But the point here is that the infrastructure that we're building, that you all are building, really powers the day-to-day operation of society today. We're at a place right now where if some fraction of our infrastructure went away, it would be more than a mere inconvenience. I remember when I was a freshman, the first large-scale internet worm took down a third of the internet. It was fourth page, 1-inch article in the San Francisco Chronicle the next day. I just imagine that happening today. Safe and secure. Hopefully I've covered this to some extent already, but this infrastructure is under constant attack, and the information that is available from compromise is of growing value, tremendous value. Similarly, though, we have to think about privacy, we have to think about confidentiality of that data, and we have to be able to encode responsibility policy in a way that the technology can enforce it automatically. Policy is local. Policy is evolving, right? Policy for the year 2000 might look very different than the policy for the year 2024, and will look different in the year 2030. And it'll also look different in one part of the world versus another. We have to be able to adapt the technology to be able to keep up with that evolving policy. Sustainability. Again, this is a place where we really have an opportunity to innovate from the ground up. Today, by some measures that I checked recently, IT accounts for somewhere between 1% and 2% of global energy consumption. But that number is on the rise. And we, again, have an opportunity as, let's say, generative AI, let's say AGI, continues to grow in scale, capability, and utility to ensure that that number perhaps stays flat, maybe even goes down. As importantly, that the sustainability, the carbon emissions in both manufacturing, delivering, and turning down that infrastructure is net zero impact. I think that these are systems problems, and they're related to how we develop this infrastructure. And finally, a big thing that happened over the past 25 years is we went from a really global distributed computing infrastructure to more centralization. I think moving forward, increasingly, sovereignty is going to be important. Maybe your personal sovereignty, sovereignty of companies, sovereignties of governments. And again, designing systems to respect that and account for that is going to mean that we're actually going to have to re-examine how we do it all. In this particular talk, I'm going to be focusing mostly on the societal infrastructure aspects and the sustainability aspects. But again, all of these are super critical. In terms of how these sea changes happen, I want to start with a little bit of history. This is an article from 1991, now 33 years ago, in the New York Times. I happen to remember this article. I know that it's a little bit older than some of you in the audience, but still, these things do happen over decades. The article was entitled "The Attack of the Killer Microbes." And the observation was that a appropriately organized set of small computers could beat large-scale supercomputers at their work. And this was for 1991, right? The age of Cray, soon thinking machines, and related companies. This was heresy. Over the next 10 or 15 years, this idea really sprouted. Right? And by 1993, when I was talking about, let's say, the birth of the widely available internet, internet services ran on single computers. Alta Vista, one of the, I would say at the time, world's best search engines, ran on one computer. Right? Web search ran on one computer. That hit scalability limitations. Right? And form followed function, and clustering took over. But the notion of having a warehouse of commodity servers running open source Linux, while we perhaps in this community take it for granted, of course that's how you do it. Conventional wisdom. I can assure you in the year 2000, 2002, this was heretical. This was massive debate, right? This was one deeply entrenched path versus another. And so what's exciting to me is just when we take this as conventional wisdom, just as we take it as the way that we must build infrastructure, it's not going to work anymore. That's a big statement I'm making, but I actually think that the data and the trends support it rather strongly. So what have we done, though? Let's say over the past 20 years in getting to commodity storage, commodity computes, commodity network hardware as the basis for planetary scale infrastructure. It's actually been spectacular. And we've ridden a wave where we've doubled performance every 2 years. Delivered performance, not per CPU performance, per core performance, but delivered performance every 2 years. Throughput, capacity, scale, for the same cost. Right? And this is all built on commodity Ethernet, cluster-based computing, centralized control was the rule. And all told, this delivered a factor of 1,000 together in scale for the same price. And this then enabled real-time communication across the planet and the access to the totality of human knowledge at your fingertips. We all take for granted that we can look up any fact, listen to any song, watch any movie instantaneously. 20 years ago, that was almost science fiction. Right? I can now translate in real time from one language to another and carry on a more or less interactive conversation with many, many people across the planet that I wouldn't have been able to. Right? For me, growing up, this was Star Trek. And now it's what we're living. Interestingly, without this, we wouldn't have artificial general intelligence. Perhaps it is this digital access to the totality of human knowledge and this 1,000x scale in compute for the same cost that's enabled us to get to this next breakthrough. Okay, form again follows function. I won't spend time on this, but it wasn't, of course, the underlying hardware organization that drew all this together, but it was also the software. And it's hard to say whether the software came first or the hardware came first. I think it's safe to say that it was a virtuous cycle. And the software became increasingly distributed, whether it was storage. Again, the notion of being able to deliver file service from tens of thousands of disks spread across tens of thousands of servers as one coherent storage infrastructure, that would have been considered heretical 20 years ago. Data analytics, cluster scheduling, large-scale databases, and of course, machine learning systems like TensorFlow followed, all following this paradigm of loosely coupled distributed compute running on commodity hardware with Ethernet connecting it together. Okay. But just as we've taken all this for granted, we have seen some really hard technology plateaus. And you all are, I think, more familiar, as familiar as anyone in the world with these plateaus. Essentially, what got us here can't carry us forward because while these are cartoons, they're actually slightly obfuscated versions of real data in terms of what we're seeing with CPU performance, the cost of DRAM per byte, the cost of disk per byte, and power efficiency, right? Compute units delivered per watt. All of these over the past few years have plateaued. In some cases, they've gone the wrong direction. So one thing to note is, spectacularly, we're still delivering a doubling in transistor count per package every 2 years. Unfortunately, the cost is going up per transistor slightly in some cases, and the power is going up slightly in some cases. It's not going down. At best, it's staying flat. So doubling in performance every couple of years is very impressive. It's most impressive when I say for the same price and power. I no longer can say for the same price or power. Right? Doubling in performance for double the cost and double the power, still good, but it's not going to get us to where we need to be. Now, juxtapose this with sincerely the biggest explosion in demand for computing that I've ever seen. Right? So this shows the increase in dense parameter count for models till about 2022, growing at 10x a year. And we know that the computation required to train models and to serve them grows superlinearly, meaning at least linearly, with the parameter count. So that says over the past, let's say, 6 years, we've had a factor of 1 million increase in demand for compute. Now, that factor of 1,000 I told you about, right, and performance normalized the cost that we delivered over 20 years was impressive. Like that kept up with a lot. It can't keep up with this. Even if we were getting the underlying trends from the transistors, it couldn't keep up with this. And so what that says is that the architecture underlying the systems that are going to do training and serving at least is going to have to radically change if we have any hope of keeping up with the demand. Okay, so dense models, just to go into a little bit of background, I'll go through this quickly. Organized in layers, many parameters, each one activated for every request, each one trained on tons and tons of data. Increasingly, so one thing to note is that the work, of course, to get to efficiency, to get to sustainability is not only going to come from the architecture community, it's going to come from the model and algorithm side, and we're going to meet in between. The point here is that the model algorithms are going to have to get more efficient. The way that we choose the data and the way that we train on data is going to have to get more efficient. But we're still going to have to do much, much better on the infrastructure side as well. Interestingly, as the algorithms change, we're of course going to have to keep up with the infrastructure rapidly. In other words, how do we make sure that we are forward-looking with our capabilities, with what the algorithms and the models are going to be delivering? So this is one example where we're looking to become much more efficient through a mixture of experts and sparsity, allowing us to activate only regions of the model as needed. So you can now imagine that today, for most deployed infrastructure, whenever you make a request for inference for serving, the entire model would get activated. So can we get to a world where actually, based on the request, we might be able to do routing within the system and go to a set of experts embedded within the larger model and activate only portions of it, leading to much higher levels of performance, ideally, because you have to access less data and you have to do less compute. But interestingly, without going into the details, how you would build the hardware to support sparse models is actually very different than how you would build the hardware to support dense models. How do we keep up adaptively in such a world? And the other thing to note as we go to perhaps trillions of parameters and beyond, and the amount of computation that's required here, the amount of parallelism and the amount of synchronous parallelism required is growing tremendously. So again, without going into the details, we're in a place right now where training takes place synchronously across, let's say, thousands, if not tens of thousands of individual accelerators. And the model is partitioned across those accelerators, right? So that's 1 degree of parallelism. The data is partitioned across those accelerators. We don't feed all the data into every accelerator. And you saw the layers. Those might also be partitioned across the accelerators as well. Now, an individual computation, I highlighted this word synchronously, runs synchronously across all of these nodes, thousands or tens of thousands of them. And for training, I actually have to complete one step before I move to the next. And what that means is the failure or slowdown of any individual node has a dramatic impact on the end-to-end performance of the system. All of distributed computing infrastructure developed over the last 20 years has been built around a single server being able to go away without affecting anything. It's been built around a single rack going away without affecting anything. In some cases, even a single building going away without impacting anything. We are, with training and serving today, very, very far away from that. Right? So in other words, individual failures can bring the entire computation to a stop. Now, if you do the math and you say, okay, maybe I have thousands or tens of thousands of elements, how often is there going to be an individual failure? You compound that with each of these individual accelerators or chips being at the absolute bleeding edge of what's humanly possible. To say is that through no fault of the individual accelerators, they fail more often than, let's say, other chips might. They're just at that very bleeding edge of packaging technology, of size, of power, of everything. So now how we design systems in a world where actually every failure matters is radically different. We'll talk about that more. Okay, so hopefully that provides the backdrop for why we must reinvent compute for this next epoch of computing. And I think that this is a really important distinction. We're at a place right now where redoing things is not a nice to have. If it were nice to have, it wouldn't happen because redoing things is really hard. We're in a place right now where literally we can't do things the way that we used to. It's just not going to work. So we must reinvent. And that's going to be, for some painful, for some others, really exciting. And I'm guessing that for most of the folks in this audience, really exciting. Huge opportunity. Okay, so now what have we done at Google to respond to some of this? We were fortunate about actually a little bit more than 10 years ago, where we had an observation that if we believed that our users would interact with our services via voice for 30 seconds a day, our active users, we would have to build 10 entire Googles just for that computing load. And we're very fortunate. We were very fortunate 10 years ago. We remain very fortunate, but that was unimaginable. So that said that even back then, computing had to be redone at least to some extent. We couldn't do it on general purpose compute. We had to build an accelerator specialized to the use case of inference for voice. And that was TPU v1. We built it, and it was actually very successful. That led to TPU v2, where we observed that actually training that data for doing inference required tremendous amounts of computation that wasn't efficiently done, or as efficiently as we'd like done on CPUs. And that led to TPU v2, which was 256 nodes interconnected by a special network to support actually just the training workloads. We introduced liquid cooling with v3 and went to 1,000 chips. With v4, actually for some of the fault tolerance reasons that I'll talk about shortly, we introduced an optically reconfigurable 3D torus to interconnect 4,000 chips. In v5, we actually built two separate systems, one specialized for, let's say, medium scale training and serving, and then v5p, which was specialized for the highest end of training workloads, in this case, 8,960 TPUs, third generation of liquid cooling and second generation of optical circuit switching, really focused on delivering performance, power efficiency, and in the end, good put, like we'll talk about again shortly. So the thing to note about TPU supercomputing, and actually, again, while I'm taking a Google-specific view, you could likely adapt many of the same thoughts to GPUs as well, or other accelerators, is that we leverage judicious specialization and heavy application co-design. So the other thing, again, going back to the history that I'll note, is that this was really the first time at any significant scale that a specialized accelerator beat out general purpose compute. Because previously, because we were getting that doubling in performance every, let's say, 18 to 24 months, most accelerators wound up losing out. They were harder to program, they took longer to deliver, and they only addressed a relatively small subset of the workloads. You'd rather have that general purpose compute that could take on 100% of your workload rather than a bunch of individual accelerators. What changed? The performance of general purpose compute plateaued, and we had this one application that, if you recall the Google voice recognition example, could be 90% of our workload. One accelerator for 90% of your workload makes a lot of sense. One accelerator for 5% of your workload actually doesn't typically make a lot of sense. So, but now how do we go about designing these accelerators? It's really, okay, what do we need to do for this domain? We build a synchronous high bandwidth interconnect supporting essentially only parameter distribution. Right? For the first time in my memory, a network that really wasn't based on Ethernet was the right way to go. This is a, let's say, a TPU to TPU interconnect designed wholly for dropping parameters from registers, essentially, on one TPU to another. No framing in common with Ethernet. It's a point-to-point network. The routing is very, very simple and super high bandwidth. So the point here is that actually integrated with the TPU is a very simple but effective switch chip that has roughly as much bandwidth as a high-end Ethernet switch. Not, to be clear, no magic here, no brilliance here, much, much less functionality relative to an Ethernet switch, but as much bandwidth and capability for the problem of parameter distribution among TPUs. We leverage liquid cooling. Right? To this point, air cooling was the only and best way to go. But to get the maximum level of performance out of these systems, liquid cooling turned out to be the right path. Optical circuit switching I'll talk about this in a little bit more detail, but essentially what we could do is we could reconfigure the 3D torus on the fly in response to failures so that we could route around individual failed elements, making the torus whole while dealing with failed element dynamically. A huge part of this has been specialized data representations. But again, what we did here was we actually had a representation of data starting with BF16, but now down to int4, FP4, specialized for just machine learning training and survey. And this has actually been a big part of the performance improvements we've delivered. We went from general purpose DRAM to high bandwidth memory that essentially was on the same package as the compute, and very specialized hardware for both scatter gather operations and dense matrix multiplication to go after just that type of compute. I won't spend much time on this, but the thing to note here is that, again, some of the technology that we've had to leverage had to be built from the ground up in ways that hadn't existed before. One of them is these optical circuit switches. What you see here on the far right of the slide is a MEMS switch. This would roughly fit on in the palm of my hand. Think of it as the size of a normal ASIC. But here there are actually hundreds of individual mirrors that are under mechanical control. So now imagine hundreds of fibers essentially plugged into a switch designed to shine the light down on this ASIC at precisely the right location, such that the mirrors rotating in 3D can reflect the light back to the right output port. The cool thing about an optical circuit switch is it doesn't need to do any electrical packet processing. Right? There's no electronics involved. It's reflecting light from an input port to an output port, but which output port can be dynamically programmed by rotating the mirror in 3D. The amount of power required for such a OCS switch is tiny, basically what's required to hold the mirror in place in 3 dimensions. And the mirrors don't care what the encoding rate is of the light. Could be 40 gig, could be 100 gig, could be 200 gig, 400 gig, and beyond. Right? So this then becomes a part of the infrastructure, not necessarily a part of that. Think of it as part of the building, as opposed to a part of the computer. Okay, so this is all taken together, right, by basically saying we're not going to make this be general purpose compute, and we're going to revisit some of the hard-won lessons from the past 20 years, has delivered about a factor of 100 in terms of performance efficiency, and certainly more than that in terms of scale. But you saw earlier that the demands for performance are closer to 1,000,000x. Right? In other words, it's insatiable. So I don't know how we're necessarily going to go from 100x to 1,000,000x, but I'll focus here on what we might do to then get to the next 100x. And I think that this then says we're going to have to go even further in thinking about how we build our systems and how we design our benchmarks and our goals in doing so. This says we should be optimizing for system goodput. Means that we should be optimizing for power, for reliability, and actually for carbon dioxide equivalent emissions in building our infrastructure. Of course, we're going to have to continue to go after the next generation of horizontal scaling. Right? This means that we're going to have to run ever larger systems reliably. And this means hardware-software co-design with the algorithms that are going to be evolving. And something for us to all be thinking about is, if there is an algorithmic breakthrough, how would we as a community enable that breakthrough to have impact at faster than, let's say, 3-year plus cadence? Right? Because the rate of innovation here and the rate of change is tremendous. Okay, so now some interesting data points. This is some of the subset of the promised hot off the presses data that I promised you early on. It turns out that with these accelerators, we're making the life of our developers, our model developers, harder over time. So bear with me, but on this time axis, on the x-axis, we have 8 systems. I've anonymized the systems just so we don't argue about the merits of one system versus another, but you'll have to trust me that they're 8 real systems. And here I'm plotting on the y-axis the number of 8-bit equivalent tera operations, right, per second that these systems deliver normalized to the memory bandwidth of the systems. So essentially, how much more compute, generation over generation, are these systems delivering relative to how much more memory bandwidth are they delivering. So starting off at 1.0, roughly, with system one, what you can see is that actually the compute capability of all these systems is growing linearly relative to the memory bandwidth. Ideally, from an algorithms design perspective, this curve would be flat. Generation over generation, if I want to build balanced systems, or let's say in 2017, I got the system balance point correct, I would say, okay, my compute to memory bandwidth ratio is X, and I'm going to try to maintain that. And this is across multiple systems, multiple types of systems, and multiple generations, have been unable to maintain that. We've been throwing more compute at the problem, maybe not surprisingly to you all, and not able, we have scaled memory bandwidth, but not nearly as much. So now a question is, in terms of delivered performance, what are the implications? We'll look at that in a moment. Same view, except this is for compute, 8-bit tera operations per second, normalized to the provisioned per chip amount of network bandwidth. And remember that all of this computation is distributed computation. It's synchronous, running across thousands of chips. So network bandwidth matters here, and oftentimes can be as much as memory bandwidth, maybe not quite as much, but almost as much as memory bandwidth, the determiner of performance. Ideally, this curve would also be flat, because we would be saying, okay, this is the right balance point for this algorithms that we're building, and we're going to try to maintain that. It's been getting worse and worse generation over generation. I haven't plotted 2024 and 2025, but the trend is going to continue, is the short version. Okay, what are the implications? So here, there's a bit here, but I think it's interesting. X-axis is operational intensity, and on a log scale, essentially, how much compute would you do per byte? And y-axis is the roof line, the best performance delivered in tera operations per second that you could hope to deliver. You built a perfect system. And what you can see is actually the systems moving up the roof line over time. They're able to support higher levels of operational intensity, right? The lowest one is system one, roughly. The highest one is system 8. So over time, you can see that things are peaking toward higher and higher levels of ideally delivered performance. But now I've also put some vertical lines here that says for different kinds of workloads, what is their inherent level of operational intensity? You can see for embedding models, the operational intensity is relatively low. That means that we're still on the steep part of the curve in terms of delivered performance. On the other hand, these embedding models maybe don't need the highest end chips to run. Decode serving, higher level of operational intensity, more math that it needs to do, right? And now it's starting to hit that boundary point between the steep part of the curve and the flat part. Training essentially is now past the needs of the curve in almost all cases, as is decode prefill. What this says is that maybe there's a bit more to do, but as we build more and more of these systems that continue to throw more compute at the problem, we're going to get to the point where that increasing amount of compute isn't going to result in increases in delivered performance rather quickly, right? So in other words, it might be another generation or two where actually the increase in performance per chip, certainly in terms of flops, let's say, or teraops, is not going to result in, even under idealized circumstances, and I really want to emphasize the roof line, delivered performance will be lower. We're not going to get the requisite benefits. So once again, this says we have to think about how we would design our systems differently. And I think that starts at some level in terms of thinking about our metrics, because our metrics today, what many focus on is chip performance with a headline number of typically floating point operations per second, normalized to the cost of the chip. But as we saw earlier, but also as we know from decades of experience with benchmarking, that doesn't tell all the story. And in some cases, it doesn't tell much of the story. So if you have chip perf to dollar as your primary metric, then higher power is okay, as long as it meets the reliability and heat dissipation requirements. You'll pack as much as you possibly can into that chip. Now, you're not going to account for system cost here as well. And for these systems, while the chip is a substantial fraction of the system cost, it's not the entirety. And then finally, our benchmarks are only really reporting performance at a given system size, not accounting for system costs, the efficiency of that infrastructure, power, carbon dioxide equivalents, or more. At Google, for some time, and I'm certain at other places, we've used the measure to evaluate our system design. It's called PerfTCO. So what PerfTCO says is that we care about the cost of the entire system, but not just the cost of acquiring the system, right? Not how much we have to write for the capital expenditures, like I have to go buy a chip, I have to go buy some sheet metal, I have to go buy some DRAM. That's a fraction of the cost. But we also care about the operating expenses associated with it. And that is the cost to actually run it from a power provisioning perspective, space provisioning perspective, and then the actual power draw. That's the denominator. The numerator is the performance delivered for a benchmark suite that we believe is representative of current and future benchmarks. Okay. So this does better than chip performance normalized to dollars, but it's actually also not nearly enough, as I'll talk about shortly. It has a bunch of hidden assumptions. One is that there is enough data center capacity to house new compute, always. In other words, it's basically saying that power is an infinite resource and that you have that space and power available to you whenever you need it, when you want to provision new compute. One way to look at it is if I have some really important workloads and I run out of power, doesn't matter what my PerfTCO was. Maybe I'd actually rather have a design that required less space, less power, and looked less good from a PerfTCO perspective, but gave me much more flexibility and much more power efficiency. Another hidden assumption is that the consumed power can accurately be attributed to individual workloads. We actually don't have the telemetry to be able to do that. And that's a chip design question. And then finally, it's really hard to have benchmarks that capture the characteristics of both present and future workloads. So I think increasingly and critically, we need to be thinking of new metrics that can capture the needs of our infrastructure moving forward. One is systems performance per average watt. So again, one of the things to consider is that we typically look at the maximum power draw of a chip. We really should be looking at the maximum power draw of a system, but more than that, we should be looking at average power and making sure that we live at the right point on the curves. I'll show some more about that as well. But essentially, imagine that I have a 10 megawatt building. That 10 megawatt building is a headline number that says, here's the maximum amount of servers that I could put into that building or accelerators, assuming that all of them were drawing their maximum power simultaneously. So in practice, that 10 megawatt building might be drawing, making up a number, 8 megawatts, 6 megawatts, 4 megawatts, depending on the efficiency of the compute packed into it. Ideally, what we would do is we provision 10 megawatts. We should actually use 10 megawatts, or at least 9 continuously, and be delivering maximum good put out of that capacity. In other words, this power infrastructure that we're building is really precious for a range of reasons. Environmental, capital efficiency, and more. We need to be getting the most out of it. And there are integer factors of efficiency on the table in doing so. So that's one. Two is systems performance delivered by normalized to carbon dioxide equivalents. And this then says, where do we place the compute infrastructure? But also, how do we build our compute infrastructure? And how do we recycle it over time? Let me give one example on the importance of carbon dioxide equivalents. According to public sources, one server, building it, not running it, building it consumes 1 to 4 tons of carbon dioxide equivalents. And also according to public sources, the offsets associated with a ton of carbon dioxide equivalents is approximately $1,000 today. So interestingly, perhaps, there is somewhere between $1,000 and $4,000 of implicit costs associated with every server. Again, rough numbers, maybe a server costs $10,000. Could be 5, could be 15. But this number then is a substantial, in most cases, hidden fraction of overall costs that probably many are not accounting for. And now, won't work through the math here. Again, according to public sources, a server running over its, let's say, expected 6-year lifetime can produce 12.5 metric tons of carbon dioxide equivalents, depending on what data center it's running in. So the end-to-end system design really matters here. Okay, so I've always been inspired by this quote: "For better or worse, benchmarks shape a field." And I think that this really does bear out here. Won't go through all the details here. We have a couple more things to cover, but I think that one note here is that we did a study, and actually there's going to be a paper that we're going to be publishing soon on this, looking at our 4th generation TPUs versus our 3rd generation TPUs. The peak teraflops per dollar comparison showed a 1.9x benefit, which is pretty reasonable. Like, we get pretty excited about that. But if you actually look at what we try to do and what we've continued to try to do over the years, is we're looking to be to the right-hand side here of the metrics, not peak teraflops per purchase price, but delivered goodput over system power, and even delivered goodput of that infrastructure normalized to the system's carbon dioxide equivalents. And so the nice thing here is that actually what we're really after is not the 1.9x on the far left, but the 7x on the second to far right, and then the 32x on the far right. This says, and this is one generation over another, right? TPU v4 versus v3. Again, I'm picking these because I have good data available for them. I think there are many similar optimization opportunities elsewhere, generation over generation, that can really make this infrastructure much more efficient and much more sustainable. Maybe top order, though, also just baseline usable. So a lot of the work that we did in reliability, a couple of aspects of this. One is the optical circuit switching that I talked about. Essentially, whenever there's a failure in our infrastructure right now, we're able to isolate that and route around it. With TPU v3, if we tried to run our workloads on more than one pod, it was essentially unusable. 2 pods was okay. 4 pods, you're starting to have very diminishing returns. This means that the scale of our computation was dramatically impacted. Whereas with the improving reliability that we were able to deliver with TPU v4, we could scale out to much larger computations, multi-pod computations running simultaneously at larger scale. Right? So delivering, let's say, up to 90% goodput. A lot of these things are hidden components, not per chip components, but system components that we've had to optimize for. Okay, so I only have a few minutes. I want to cover maybe 2 things, and then maybe leave some time for questions. One is this curve here on the left-hand side, which is peak watts of a workload with training throughputs on the y-axis. This is not a new idea for this community, but I think it's one that maybe we've lost sight of a little bit, which is we should be designing our systems and designing our workloads to run at the knee of the curve of their delivered goodput per watt. Right now, we say that even if we go past the knee of the curve and we get incremental benefit for a given workload relative to the power that it consumes, we say keep going as far to the right as you can. Right? Double the power, 1% more performance. That's 1% more performance. That's the wrong way to do it. Right? Power is a finite capacity. We have many workloads, and we should be able to pick that dynamic operating points in this curve so that we can pack in as much goodput as possible within our buildings, within our campuses. Right? And we should provision only that amount of power per workload. Right? This, again, is going to require telemetry that doesn't exist, control systems that don't exist, scheduling systems that don't exist. But I think, again, integer factors in efficiency that are possible relative to just looking at what I can get for a particular workload's maximum performance. Okay. There's some interesting observations here in what we would do to co-schedule memory-bound workloads versus compute-bound workloads, delivering more aggregate performance for less consumed power. I won't go through this for time. There is really interesting work that can be done at the cluster level, accounting for the dynamics of individual, what are called bus ducts that might be at the granularity of 1 or 2 megawatts, and the dynamics of power availability on those bus ducts. I'm going to skip that as well. What I do want to spend a moment on, because we're seeing this is actually a really critical issue for us across all accelerators and even general purpose compute, is silent data corruption. This is one of perhaps the hardest things that we're dealing with right now in large scale compute. Essentially, again, with these very, very high-end chips, all of them, CPUs, TPUs, and more, there is some small probability that due to, let's say, a silicon defect that couldn't get qualified pre-screening, you might get a 1 + 1 = 3 error silently. We see these things, and so over time here, you can see we calculate the gradient norm of one step to another, where the gradient norm in general should be small. Due to silent data corruption, it can be large. What this means is that, let's say, out of 1,000, 2,000, 10,000, 20,000 chips, one of them made an error, perhaps repeatedly, corrupting data. This is synchronous computation running across tens of thousands of chips. One bad computation across quadrillions screws up the entire infrastructure. Right? We have to be able to detect these, react to them. Ideally, they shouldn't happen in the first place. That turns out to be really hard. So when they do, though, how do we recover? One, we have to be taking checkpoints all the time. Right? These happen with sufficient regularity that we can't say, well, go to the beginning of the computation from 2 months ago and start over. We have to say, okay, what was the last checkpoint? But generating those checkpoints is pretty expensive. Detecting these things and recovering from them is also very expensive. So again, if I were to say one exciting area of research is how would we really improve the reliability of these chips, but accepting some level of baseline unreliability, how would we detect and react to them? What we do right now is we again leverage our optical circuit switch to isolate suspected bad chips, rerun computation to see if there is a repeatable issue. Assuming that there is, we continue the computation from the last checkpoints without, of course, the bad chip in line, and then do repairs asynchronously. But this is I would say, a huge hit in terms of the delivered goodput, right, of our infrastructure. At the overhead of checkpoint, restart, isolate, detect, etc., very substantial. Okay, so I want to leave time for some questions, but hopefully you've seen, and what I'd really emphasize is this word required. Radical reinvention is required. The way that we do systems, the way that we do infrastructure must change. I can't say exactly how it's going to change, but I can with some confidence say that it's going to look very, very different 5 or 10 years from now than it does today. And I wouldn't have said that 5 or 10 years ago. I would have said, well, it's going to be sort of faster, cheaper, better. But now it's going to look really, really different. I think that's a safe assumption. Machine learning has already dramatically changed our approach to system design. And I think that actually that needs to accelerate. I do want to go back to the rather profound societal implications and need for accounting for responsibility and safety in our systems capabilities and design moving forward as well. Okay, with that, I can take some questions. Thank you.
Thanks, Amin. Anand Subramaniam from Penn State. Nice talk. My question was, you never talked about the energy infrastructure. You never talked about the energy infrastructure. The problem with many of these data centers is the growth really is in urban centers where renewables can't really get to, right? I mean, even in the US, it's around the DC metro area, and the most rapid growth right now is in India and so on, right? And there, forget about compute infrastructure, even the PUE is nowhere close to 1.2. It's like 1.5 or so, right?
Correct. Yeah.
So what's your thought on this modular nuclear reactors? I think that seems to be the cleanest way to do it.
I won't talk about nuclear reactors in this talk. What I will say is that we're designing our data centers, continuing to design our data centers at about the 1.8 1 or lower PUE, and actually not going into the large urban centers by default. So much of the large scale computes is continuing to meet our goals of getting to net zero, separate conversation, by 2030.
Great talk. I mean,
Mark Hill, University of Wisconsin Emeritus. Hi, I mean, so people in industry often ask academics to estimate total cost of ownership. How would you recommend they do that without swags that get them pillared by referees?
I think that this might be a great opportunity to say we don't care about total cost of ownership anymore. We care about the total power consumed by a given workload, which universities are in a much better position to measure. And I would actually endorse that as a mostly industrial person.
Great talk. I'm Isha Choksey from Azure Research, and every day I live and breathe the power bottleneck in generative AI, so love the talk. We have a lot of hardware options in the market when it comes to better power at the okay performance level, right? And the main problem tends to be the software stack availability when it comes to optimization. So what are your views on that, and how can we work better towards it?
Yeah, I'll repeat the question. So the question is saying power is a serious issue, but how would we actually think about the software stack that makes it possible for us to leverage other hardware platforms that might deliver different optimization points in the performance to power ratio? I think it's a great question. Separate talk and separate work. We have some work ongoing in 2 systems, open source systems called JAX, which is a framework for ML development, and XLA, which is a compiler for mapping essentially the framework code to different platforms. Actually, a number of different companies, including NVIDIA, Azure, Microsoft, AWS, and others are contributing. So I do think that actually we need to get to a place where the C++, the Java compiler, the C++ compiler is, if not standard, then available across platforms. I agree with you that making sure that we can take advantage of different hardware architectures with our existing code base is really, really important to this work.
Hello. Thank you for the great talk. This is Ayan from EPFL. So the algorithms behind these models are still changing. And we have a mixture of experts. We have different sparse topologies, number formats, and sometimes maybe even new model architectures coming up. So how do you expect hardware specialization to keep up with these varying demands from the algorithm side?
Yeah, it's a fantastic question, and one that we think about also quite a bit. I didn't have a chance to cover it, but I think that the hardware development lifecycle and the process for getting hardware out there is actually a major bottleneck to where we are right now, because from idea to production is roughly 2 years today, and that would be fast. And as you said, these models and algorithms are changing very, very quickly. I think actually coming up with new development environments, new testing methods, and actually some of my colleagues are working for ML, really shortening that life cycle is going to be critically important. One key bottleneck to account for, though, however, is that within that 2-year lifetime of idea to production, there's at least 5 months for tape out to first silicon. And that one is and first silicon to working in lab is often a couple of months. So there's this 7-month period that is really, really hard to optimize, right? That basically says the process of creating a chip, especially at the high end, talking 3 nanometers, et cetera, is a inherently long process today. But that doesn't mean that the design verification cycle, which can be substantial, and then the qualification of the hardware and the software running on top of that first, let's say, ASIC, shouldn't be and couldn't be substantially shortened. And again, I think that would be really important work. Imagine being able to iterate every 1 year instead of every 2 years, right? Twice the iterations would be spectacular.
Okay, thank you.
Hi, Amin. Thank you for the great talk, and thank you for reaching out to the research community. I'm Moin Qureshi from Georgia Tech. You talked a lot about ML computation that tends to be somewhat regular, requires a lot of compute. On the other end is compute that's not as regular, right? The traditional bread and butter, the search and the things that drive the conventional servers. What I want to ask you is, how much is the synergy of what you learned from ML towards non-ML? And second, how much is the starvation, given that resources are always limited? How much is the growth here is sort of stalling the growth there?
Right. So the general purpose compute, it's a great question. And thanks for asking it. General purpose compute is going to continue to grow. And of course, from an Amdahl's first law perspective, we can't have that be the bottleneck. We look at this closely. We're at a place right now, though, where the demand for general purpose compute is more modest. Interestingly, the equation over the past, let's say, 10 years has been more toward how quickly can you have software velocity rather than software efficiency. So the implications of that for general purpose compute is actually the amount of software optimization that you can do has built up over time, right? Because given just the correct trends in industry, you'd rather launch a new feature than make your existing code more efficient. That equation has shifted, which says that actually much of what I described in terms of systems goodput per watt for general purpose compute, huge opportunity. Just one not to be ignored, actually, because it turns out of that 1 or 2% of global IT power, of the global power that's consumed by IT, most of it is still general purpose compute. The fastest growing, of course, is ML.
Good. Thank you.
So we'll have one last question.
Hi, it's Noman Bashir from MIT, and my question kind of follows up with the last question, and it is that, so improving energy efficiency reduces cost makes sense. Now performance per unit of power also makes sense because data centers cannot be deployed, grid is constrained. How do you think improving performance per unit of carbon, or that, like what kind of incentive would be there to do that?
I think there's a couple of things. One is there is a relationship between watts and carbon dioxide equivalents. So in other words, power, there is that clear relationship, but during the runtime. And companies like Google, but not just Google, have important goals to essentially get those carbon dioxide equivalents for the operational costs towards zero, net zero. And that's, I think, very important in terms of how we do our systems design, but also to get there, there's going to be needed breakthroughs in terms of leveraging wind and solar that actually haven't been invented yet. But the final bit, though, that I want to bring some light to is the life cycle in terms of constructing the material and then turning it down. Those, as we continue to, let's say we get to net zero, those other components are going to now start dominating at the birth and death, let's say, of the infrastructure. This is the community that can bring that to light, just quantifying it accurately and coming up with, I would bet, I don't know, but I would bet with some high confidence even, is that if we were to just actually quantify it, there'd be substantial, quote unquote, easy optimization opportunities for reducing the let's say, construction carbon costs and the turn down. I don't think that people are looking at it. You don't optimize what you don't quantify.
Thank you.
Yeah.
Thank you so much.
Thank you all.